Hello student, today we are going to derive a Clausius-Clapeyron equation. This equation is very important for the examination of point of view, and let us derive this equation. The free energy is given by dg is equal to v dot dp minus s dot dt. This is equation 1. Consider the system consisting of a two-phase first and phase second. Suppose that free energy of a phase first is G1 and that of phase second is G2. The temperature of the system is changed from T to T plus dt and pressure from P plus P plus dt. Only little amount of temperature is added from so that temperature changes from T to T plus dt, and a very less amount of pressure is added so that changes so that P to P plus dp. Suppose the corresponding change in free energy phase first to dg1 and that of phase second is dg2. The phase first is g1 and phase second is g2, and the uh, a very little amount of free energy is added, that is g plus dg1. This is first was in phase second the g2 plus dg2. Then according to the equation 1, and for initial state, this is for initial state, for initial, for final. For initial state, dg1 is equal to v dot dp minus s1 dot dt. Similarly, dg2 is equal to v2 dot dp minus s2 dot dt. This is equation 3, where v1 and v2 are the molar volumes, s1 and s2 are the entropies. When phase first is in equilibrium with phase second, when this phase first is in equilibrium with phase second, then del g is equal to 0. The change in g is 0. There is no change. It means that is g2 minus g1 is equal to 0. Therefore, g1 and g2 are the molar free energy for phase first and phase second. This g2 is molar free energy for phase second, and g1 is molar free energy for phase first. And from this relation, what we derive, g2 is equal to g1 and dg1 is equal to dg2. Substituting the value of dg1 and dg2 in equation 2 and equation 3. When you substitute this value of dg1 and dg2 in equation 2 and 3, then what you get, the relation is that later dg1, it was dg2 is equal to v2 dot dp minus s2 dot dt is equal to v1 dot dp minus s1 dot dt. It comes as it is, and now v2 dot dp minus this v1 dot dp comes this side, v1 dot dp is equal to this comes left side, right side, s2 minus dot dt, s1 dot dt, and here dp is take common, then v2 minus v1 is equal to s2 minus s1, and this is dt and this is dp, and now dp by dt is equal to s2 minus s1 by v2 minus v1, and dp by dt is equal to s2 minus s1 by v2 minus v1. Therefore, what you get as this s2 minus s1 means del s and v2 minus v1 is del v. Therefore, dp by dt is equal to del s by del v. Del v is equal to v2 minus v1 is equal to molar volume changes, and del s is equal to s2 minus s1 is equal to molar entropy changes. When phase first change into phase second, if this change occurs at the temperature T, that is melting point, and del H latent heat of transformation, then del S is equal to del S by T, equation VI E. Then putting the value of del S in equation V, we put this value in equation V, then we get the result del P by del T is equal to del S by T dot del V. What was the question was that dp by dt is equal to del s by del v. This is the equation, And B, it was the equation B. When you put the value of IV, equation del S is equal to, we put the value of del S is equal to del S by T, then del V is from here, then we get the result dP by dt is equal to del S is equal to T dot dP. This is equation bi. This equation was first derived by Clapeyron and is called Clapeyron equation. It can be applied to various physical equilibrium like melting, vaporization, and sublimation. Let us check for melting equilibrium. For melting equilibrium, solid changes into liquid. Solid melt into liquid, or liquid may again changes into solid form. That is del S is equal to del Hm. Del Sm is equal to latent heat of melting, and here T changes into Tm. That is Tm is equal to melting point of solid, and it can be also written as dP by dt is equal to del Hm. Instead of T we write Tm, and del V is there, where del V is equal to Bl minus Bs. B means volume of a liquid minus volume of a solid. Bl means volume of a liquid minus volume of solid. Bl is equal to molar volume of a liquid. Bs is equal to molar volume of a solid. This equation 8 can be written as, we can write this equation as like this: dP by dt is equal to del Hm by Tm Bl minus Bs, volume of a liquid minus volume of a solid. This del V changes into Bl minus Bs. This equation gives the variation of a melting point with pressure. For the vibrations of equilibrium, liquid it changes into vapor, or vapor may change into liquid. Then equation 8 may takes the form, again it may takes the form for the vibration. It may takes the form dP by dt is equal to del SV. Del SV, del H changes into del SV for vibration, and TB BV minus VL, where del SV, this is del SV is equal to latent heat of vibration, and Tp is equal to boiling point of a liquid, and Bl is equal to molar volume of a liquid, and Bv is equal to molar volume of a vapor. And V is very this molar volume of a vapor is very greater than molar volume of a liquid, so Bl can be neglected. This Bl is neglected, and hence equation Ix can be written as dP by dt is equal to del Sv by Tb dot Bv. Bv, for 1 mole of a gas, Pv is equal to RT, and this Pv is equal to RT by P. It is taken as equation Xi. Putting the value of Xi in X, if we put this value of Xi, in X, then we get the result dP by dt is equal to del Sv by Tb dot RT. Instead of Vv, we put the value of RT by P. Then dP by dt is equal to del Sv dot P by, this is RT square. This here we can write Tb is equal to T. If 1 by P is equal to, then 1 by P, P came this side, this left side, then 1 by P dot dP by dt is equal to del Sv by RT square. Then this, what we know does is this dP by P, is equal to dlnp. This is dlnp, and this dlnp is here, dt is as it is remain, then del Sv by RT square. Then dlnp by dt is equal to del Sv by, this is RT square. We have written this same. This is xii. This equation is called Clausius-Clapeyron equation. Also, what we know is that dlnp is equal to del Sv by RT square, and this T comes this side. We have the cross multiplication, it comes this side, dt. Then integrating the above equation from initial state to final state. This is pressure is here and temperature is here, so we integrate it in the form of pressure. This is initial pressure P1 and this is final pressure P2, and this is initial temperature T1 and this is final temperature T2. Then what you get, d ln P is equal to ln P2 minus ln P wall. When you integrate it, we get this result, and del S B by R is here, and this we integrate in the form of a temperature, and dt by this 1 by t square temperature. Then this ln P2 minus ln P1 means ln P2 by P1 is equal to del S B by R, and this is 1 by T1 minus 1 by T2. Changing the natural logarithm to the logarithm to base, then we get, as you know, this ln is equal to 2.303 log, and instead of ln we write 2.303 log P2 by P1 is equal to del SB. This is del SB by R, and this we have done, this LCM we have taken T2 dot T1 L22 minus T1 is here. Then log P2 by P1 is equal to this one, this side cross multiplication del SB by 2.303, this is R, to this R, and T2 minus T1 by T1 dot T2. This is the called integrated form of Clausius-Clapeyron equation, and has number of applications. Applications of a Clausius-Clapeyron equation: if the vapor pressure and latent heat of vaporization of the liquid is known at one particular temperature, the value at any other temperature can be calculated. Then log P2 by P1 is equal to, if the vapor pressure and latent heat of vaporization of the liquid is known at one particular temperature, the value of any other temperature can be calculated. Now, look here, log P2 by P1 is equal to del SB by 2.303 R and 1 by T1 minus 1 by T2. This is, if we know the any pressure or at any temperature, then we can calculate the other pressure at other temperature. If the boiling point of the liquid and latent heat of vaporization is known at one particular temperature, if the boiling point of a liquid in latent heat of vaporization is known at one particular pressure, the value of any other pressure can be calculated. If the vapor pressure of a liquid at any temperature are known, then the latent heat of vaporization of the liquid can be calculated. These are the applications of Clausius-Clapeyron equation. I hope, student, you understand my class. Please like, comment, and don't forget to subscribe my channel. Thanks for watching this video.